This is video 27 in the lectures on the design of reinforced concrete beams. This lecture explains the use of lap and anchorage lengths of rebars. We will first handle the anchorage lengths and the lap lengths. When you have a cross-section and you put individual rebars in the cross-section, then the clear distance between two bars should be bigger than the diameter of the bar used, the maximum aggregate size plus 5 millimeters or 20 millimeters. Now we will see that using rebars bigger than 32 millimeters is not recommended, and it's not common used. So for most buildings, the diameter is smaller or equal to 32 millimeters. Aggregate size is the same. For aggregate size, in most cases, it's smaller than 32 millimeters. So this is 32 plus 5 is 37 and 20 millimeters. So if we keep the clear distance of the rebars greater than or equal than 40 millimeters, then in most cases we are correct. So that's what I recommend. Always use a clear distance of 40 millimeters between the rebars. If you have a beam simply supported, subjected to a bending moment or inverse distributed load, then we can have a bending moment, a maximum bending moment. You put reinforcement in it, and suppose that we have in total 6 bars. And those 6 bars are put in 3 layers, or it's represented here in 3 layers, but it's not necessary. There's different layers. So now you can have 2 bars and then another 2 bars and then another 2 bars, in total 6. So you don't need the 6 bars for covering the maximum bending moment. You don't need it in all sections. In this section you need only 4 rebars, in this section only 2. So if you adapt the amount of reinforcement in the cross sections to take account of the varying bending moment, we call that curtailment of the reinforcement. If you have a continuous beam, you can see easily for the bending moment in the field, you have the first layer of the first length of bending reinforcement, and then a second layer covering the maximum bending moment. The first layer is covering the bending moment until here, until this line. The same happened with the bending moments on top of it. So you can cut off your reinforcement and use only the reinforcement where really needed. So you save some reinforcement. In doing so, we know that the maximum standard length of rebars is 12 to 14 meters. I'm not talking about reinforcement on rolls, because that exists too. So, but the standard length is 12 or 14 meters. Also, you need to transport them. So, but if you have a beam which is, for instance, 20 meters long, then you have a problem. So you have to overlap the reinforcement, and we call this the lap length. At the end, you have to anchor the rebar, so you have also an anchorage length. So there's a difference between anchorage length and lap length. Now let's talk about the anchorage length. You have here a surface of a concrete element. There's a rebar in it. I'm going to pull on the rebar with a force NS, and this force is equal to the stress in the rebar, which is sigma S, multiplied by the area of the rebar, PV squared divided by 4. So that's the pulling force. Now there's a reaction, a resistance. The resistance is NR, and the resistance, the only resistance that we can imagine is the surface of the rebar multiplied by the shear force, multiplied by the shear stress. So you have the surface of the rebar multiplied by the shear stress. Now, in an equilibrium, they must be equal. If you put in the numbers and you solve it for the length LB, then you know if your length LB is equal to phi over 4 multiplied by the steel stress divided by the bond stress, then you have an equilibrium and the rebar will stay in the concrete. So this is important to notice that the anchorage length is proportional to the stress applied in the rebar. And it is also proportional to the diameter of the rebar. Now look at the ultimate bond stress, because this is still an unknown, the tau, or here in the proper name is FBD. That's the ultimate bond stress. Is 2.25 multiplied by 2 coefficients and by FCTD, which is the design tensile strength of the concrete. And because this is working in favor, we don't take the mean value, but the lower 95% limit. So it's 0.7 times 0.3 times FCK to the power 2/3 divided by gamma C. So this is FCTM. It's 0.7 FCTM. Eta 2 is a factor taking into account the size of the rebar. When the rebar is smaller than 32, it's 1. Otherwise, it's this formula. And N1, it's a coefficient taking into account the position of the rebar. The position of the rebar is considered bad when it's in the top of the construction. And for H bigger than 250 millimeters, this is defined as a bad zone. And then N eta 1 is 0.7. The basic anchorage length is LB required, RQD, LB required. We have seen this formula, we know that now. Sigma S is now replaced by sigma SD, the design value of the tensile stress in the reinforcement of which you want to calculate the lap length or the anchorage length, and FBD is the bond stress. And it's same as the tau that we had previously. So the design value of an anchorage length is then divided as a multiplication of 5 coefficients, the basic anchorage length, and must always be bigger than a certain limit. And this minimum limit is for tension equals 0.3 lb required, 10 phi or 100 millimeters. So you can never have an anchorage length smaller than 10 times the diameter of the bar, never. And for compression, these are the values that are there for compression. In this formula, if we look at it a little bit closer, then there is also a limit put on alpha 2, alpha 3, and alpha 5. If you multiply them, it must always be bigger than 0.7. If this is not the case, you can replace it by 0.7. The first factor, alpha 1, is the shape factor. The second one is concrete cover, is dependent on the concrete cover. The third one deals with confinement of the concrete. Alpha 4 has to do with the type of load, tension or compression. And alpha 5 is the lateral support that it has. So these are the 5 phenomena that govern the anchorage length. This is now the coefficient alpha 1. You can have in tension and in compression, and it has to deal with the influencing factor is the shape of the bar. So when the bar is straight, then alpha 1 is 1, and when the bar is different than straight, then alpha 1 is 0.7. And there's also a factor CD, and this factor CD is given in those drawings. You have just to apply it. Then alpha 2 is the influencing factor, is the concrete cover, and you will see alpha 2 is a function of CD again, that we've seen in the previous slide. Must always be bigger than 0.7 and smaller than 1. In compression, it's always 1. And this is for straight bars, and this is for other than straight bars. So it's always the same, is the factor CD comes into the formula. And alpha 3 is a factor, is a function of K and lambda. Lambda has to do with the surrounding reinforcement, and K is a factor which is indicated here in the drawings, depending on the position, that's the red bullet, depending on the position of your reinforcement. And alpha 4 has to do with confinement. Most of the time alpha 4 is 0.7. Then we have also the 25% support rule for the tension reinforcement. It means that at the supports, at least 25% of the total reinforcement for the maximum bending moment of that beam must continue over the support. So at least 25% of the maximum reinforcement in the beam. Another rule at the support is that the total reaction force at the support must be smaller or equal to the shear resistance of the longitudinal reinforcement at the support. It means that the rebars only must take the support reaction only by shear resistance. So now we are sure that we are safe that the beam is not coming down. So it means in numbers that the reaction of the support must be bigger than the total amount of reinforcement multiplied by FAD divided by the square root of 3. So the minimum amount of reinforcement at the support is or the minimum reinforcement or the reinforcement needed to take a bending moment. If it's fixed support, then there's a bending moment, or 25% of the reinforcement in the other parts of the beam, or it's the shear required reinforcement. The anchorage length now in function of FCK and phi can be expressed like it is indicated here with some assumptions with the position and so on, but in most common cases you can work the formula out and then you find that the required anchorage length is 345 times FCK to the power 2/3 multiplied by the diameter of the rebar you are using. This, of course, is working with the maximum stress in the rebar. It means it's working at 435 megapascal. This rule can be useful to have a first estimate of the anchorage length. If you now take a concrete C2530, then you see that the anchorage length is 40 times the diameter. This is a common use number on site, but this is only valid for a concrete quality C2530 and for steel working on its maximum stress capacity. If you take C3037, then the anchorage length is 37 times the diameter. Now we will tell something about lap lengths. If you have a large beam bigger than 14 meters, you need somewhere a lap to produce a lap, the lap length, and the laps should always be in different cross sections. So if you have 2 bars in a cross section with a lap length, then don't make them here in the same cross section. Put a lap length there and a lap length here. And also try to make or do the laps in the least loaded cross section. For lap lengths, bars in one layer, they can be 100% lap bars in tension, that's permissible, and bars in several layers, it's only maximum 50% of the lap bars in tension is permissible. There are all kind of rules. The distance, if you have 2 bars overlapping, then the distance between those 2 bars, the clear distance must always be smaller than 4 times the diameter of the bar. If not, then you have to add with your lap length, this distance you have to add to your lap length. This is for the percentage of laps in the same section. The drawing is clear how to use it, and alpha 6 is a coefficient that's taken into account the percentage of lap bars relative to the total cross-section area. In fact, alpha 6 is given by this formula. And the percentage of lap length can be found by means of this drawing. For diameters bigger than 20 millimeters, there must be a check because of at the lap length, to check to see if the transversal reinforcement is there and is big enough in tension and in compression. So for diameters bigger than 20, you always need a transversal reinforcement. Now the formula for lap length is also a multiplication of a couple of terms multiplied by LB required. LB required is the same as that we have seen previously. It must be bigger than L0 min, and the L0 min is 200 millimeters, 15 times the diameter. So you see that the lap length is at least 15 times the diameter. An anchorage length was at least 10 times the diameter. So you have there a difference in coefficient between those two, or 0.3 alpha 6 LB required. If you take for the most common cases and you work this formula, then you see that the design value of the lap length is 519 divided by FCK to the power 2/3 times V. Again, this is assumed that the steel is working at 435 megapascal. If you take a concrete quality of 25, you got 60 times the diameter, and a concrete quality of 30, you have 54 times the diameter. We've seen now, this is the anchorage length. This is the lap length for most common cases. So you see that the lap length is the lap length is 1.5 times the anchorage length. In most cases, in most common cases. When you're using a welded mesh fabric as a main reinforcement, then you can have a lap length by intermeshing. It means that you put two meshes, one on top of the other, but you turn it around so that one rebar is laying in the same layer as the other rebar. So this mesh is just turned upside down regarding this mesh. Or this intermeshing is used or is needed for fatigue purposes. And you can also layer it. It means you just put it one on top of the other, but you see that you lose distance. So it's better that you turn this upside down. And then you can use laps 100% if the AS over S provided is smaller than 1200 square millimeters per meter, or otherwise it is 60%. Alpha 3 is always 1 because we do not take confinement in consideration with welded fabric meshes. Then for welded mesh fabric distribution reinforcement, if it's not the main reinforcement but distribution reinforcement, then there are also some rules which are less severe. There are special rules for large diameter bars. That means for bars diameters bigger than 32 millimeters. In fact, a lap length for such bars are not allowed. It's only allowed if your steel stress is smaller than 0.8 FID in ULS, or the smallest dimension must be bigger than 1 meter. So if you use lap lengths, you use a lot of capacity of your reinforcement. And anchorage, for anchorage length, it should always be mechanical. So with bolts or welded. And you need, If you use big diameters bar, you need surrounding reinforcement to take care of the splitting forces of the concrete due to that large diameter bar. So it's rather complicated and difficult on site. If you use, for instance, a diameter 40, then you need all those surplus reinforcement and you lose capacity. Therefore, I strongly recommend do not use rebars with diameter 40 millimeter or greater for common buildings. For large infrastructure works, that's something else. But for common building, don't use rebars with a diameter 40 or greater. You know now that the lap and anchorage length is proportional to the steel stress and that the lap length is twice the anchorage length. See you at next lecture.